All right, I guess some of you have been working on the peptides during the break, so that's good. I've heard some cries of frustration. You get all the way to the end and you miss one. If you do it on your iPad, that's a real easy problem to fix, but if only. Okay. So this is just a way to test how well you know the amino acid structures. We can answer the charge question easily without drawing the structures if you remember that the negatively charged amino acids at pH 7 are D and E, aspartate and glutamate, and the positively charged ones at pH 7 are K and R. If you remember at pH 2, there are no negative charged amino acids, and the positively charged ones should include K, R, and H. So if you know the structures and you can read a pKa table, you can figure all of that out. But if you want to memorize quick rules of thumb to help you out, that can be helpful too. Also, don't forget the N and the C termini. All right, so the N terminus is usually a positively charged ammonium group, and the C terminus is usually a negatively charged carboxylate group, though that could change as a function of pH. So what do you want to do? Should we draw one of them together? I mean, or is that a waste of time? I don't know. I wrote the quiz, so we can do it. All right, proline is a weird one. Remember, proline is the one where it's a 5-membered ring side chain that links back to the nitrogen. At pH 7, that N-terminal amino group should be positively charged. To get this right, and the way this would work on a multiple choice test is actually I would write the sequence palpatine lives, and then I would have options A through H or something that were, and only one of them would be right. And the ways I would draw incorrect peptides are, I would have the wrong stereochemistry at some or all of the amino acids. I would draw the wrong amino acid in place of a letter. So for example, if you get glutamine and asparagine mixed up, you can bet I'm gonna mix that up on the exam. I would also mix up, remember when you write sequences, you must also write them N to C. So I would draw the peptide backwards. I would make it look like it says palpatine lives, but I would be starting on this side on the left at the C terminus. And so there are a lot of different ways I can lie in wait to deceive you. Okay? So you got to get the structure right, the side chain stereochemistry right, and you got to have N to C in the correct orientation. It's easiest when you draw it. If you will always in your peptide, draw the N-terminus on the left. That way you can follow along with the sequence. For a peptide that's drawn for you, look for the amino group or the ammonium group at the C-terminus, at the N-terminus. Draw an N there, then draw an arrow to the other one where the carboxylate terminus is and write a C. That'll help you keep things oriented. And remember, if you're going to write down the sequence, you got to write it down N to C. Okay, so there's proline. Alanine, tell me what the correct stereochemistry is at the alpha carbon. Should be a dash or a wedge? Wedge. And what is the side chain for alanine? Just the methyl group. Okay, and I can already tell we're probably going to run out of space, so maybe I need to make my drawing just a little smaller.
You will.
I will. You've done this before. I already did it.
Good thing you have an iPad.
Good thing I have an iPad, yeah. Okay, what about, let's got to decrease the font size now. All right, leucine. It's going to be a wedge now, and the beta carbon is attached to another carbon, which is itself a branch point. Okay, that's leucine. Then we need another proline. For proline, when it's in a peptide, we just sort of draw it like that. There's no H on that nitrogen. Yes?
Would it, like, if you were to draw it, I guess, what if it were to space itself out, would it bend the peptide?
Yeah, so you might think I'm sort of cramming it in there, and perhaps better way of thinking about what the structure of proline would do. Sorry. Oh, what happened there? I don't know what happened there. Thinking about what proline would do is it would tend to kink the chain so as to be not linear. This drawing is just to get all the connectivity correct. You're not required, and the stereochemistry correct, you're not required to draw a physically realistic conformation. So you could draw it like that for the sake of making it really sort of easy and zigzaggy. I'm just gonna do this, recognizing that that may not be the actual shape it adopts. So P-A-L-P, then I need another A. We already know what A is. And then I need a T. Threonine, what is its side chain structure?
Wait, does the A have another bond on it? Or am I going crazy?
Let me just
Then wouldn't that be
P-A-L-P-A. Sorry, I'm not seeing it, but that doesn't mean anything. So tell me what's wrong.
on the A? Is that G? Does that mean G? On the first A, would it have another bond to the
This first A should have it. You think should have another bond where?
carbon?
Here's carbonyl carbon, alpha carbon, beta carbon. G would have no side chain, meaning at the alpha carbon you'd have 2 protons. If you want, you can draw the other hydrogens on the alpha carbons. Is that
I think I was just confused.
okay? You're not required to draw the alpha protons, but you can do so if that would help. All right, there's pal, and then we need a T. What is the identity of threonine? Methyl and yeah, alcohol. And though that beta carbon is a stereocenter, I'm not requiring you to know what that stereocenter's configuration is, okay? Then we need an I, isoleucine. So how does that differ from leucine? Methyl and ethyl on that beta carbon. Good. And again, that is beta carbon is a stereocenter. We're not going to care about which is the right one. I've probably drawn it wrong. Did I draw it wrong?
No, I was just wondering if the ethyl was on the other side.
It might be. I always, the configuration of isoleucine is supposed to be S at the beta carbon. So 1, 2, 3. Yeah, I've drawn it wrong. If you want to draw it like this, put the ethyl on the right. But anyway, I'm not going to be testing you or attempting to deceive you on that. So that's an I. Then we need an N. This is one of the weird ones where the N doesn't have that much to do with its structure. So that's asparagine. That's a beta carbon and then a carbonyl carbon and an NH2 group. Importantly, asparagine is an amide, not an amine. And this is something that actually in retrospect caused several of you problems on the most recent exam. Some of you looked at that at an asparagine side chain. You didn't know that's what it was called then, but it is. And you're like, hey, that's an amino group. And the answer is it's not. because the lone pairs on the nitrogen are delocalized with the adjacent carbonyl oxygen. They're involved in resonance. So asparagine is not very basic, so it doesn't act like an amine. It does not pick up a proton. That's why its pKa isn't on the list. Okay. So then we need an E. E is one of the weird ones. Its name has nothing to do with, well, not one of the weird ones, but just one of the ones whose name doesn't have anything to do with its structure. E is glutamate. At pH 7, it should be negatively charged because the side chain pKa is around 4. So we just spelled palpatine. Yay. We're almost there-ish. 1, 2, 3, 4, 5, 6, 7, 8, 9 so far. Okay, then we need another L. Notice that when I draw the peptide in an extended fashion, and I've got the stereochemistry correct, we've sort of got alternating, right? It's a wedge here, it's a dash for the next one, it's a wedge, it's a dash for the next one. Just, again, make sure that they all have the correct stereochemistry. L should be this. By the way, it doesn't matter which direction I point the side chain. You can rotate freely around carbon-carbon bonds, especially the bond between the alpha and the beta carbon. So it doesn't matter which side the rest of the side chain goes on. That's L. Then we got another I. Then you got V for valine. Another E for glutamate. And then lastly is serine. What is the serine side chain? Yep, beta carbon and then an OH. Palpatine lives. All right. So if we look at the overall charge on the molecule, I got a plus on the N terminus. I don't have any other pluses. And then I got 1, 2, 3 minuses. Again, remembering that at pH 7, carboxylate side chains are going to be negatively charged. They don't get neutral until you get the pH below 4, which is their pKa. So our overall charge should be 2 minus. The positively charged N terminus offsets the negatively charged C terminus, and then the 2 glutamates give you your negative charge. Okay, so a couple of questions that can come out of peptides and amino acids are, I could show you a structure and say, what is the sequence? Or I could give you a sequence and have you choose the correct structure. I could also give you a sequence and say, what is its net charge at pH 2 or pH 7? Questions about that? Yeah?
I'm just a little confused about the charge. So if we were to do the exact same sequence in a pH 2,
All right, so let's talk about at pH 2. This is pH 7. If we wanted to ask at pH 2, we need to just remember first what the pKa's of the various groups are. This is an acidic group that can lose a proton to become neutral amine, and that pKa is around 11. So it actually doesn't matter whether we're at pH 7 or pH 2. This group is going to be in its positively charged form either way. Does that make sense? All right, let's look at the carboxylic acids. They are conjugate bases, the carboxylates. They are conjugate bases of acidic groups that are neutral. And the pKa for the carboxylate side chain is 4. So that's tricky because at pH 7 they should be negatively charged. At pH 2 they should be neutral. And that would be the same over here. Now what do we do with the C terminus? As I told you last time, and I don't really think I would expect you to memorize this, the C-terminal carboxylate group has a slightly lower pKa. The presence of the alpha amino group increases its acidity, and that pH is around 2. So technically, it'd be a 1-to-1 if when pH equals pKa, acid and conjugate base are equal in equal amounts. Just so you don't have to memorize a different number, we're going to treat the C-terminal amino acid carboxylate, if it's there, the carboxylate, we're gonna pretend that the pKa is 4. So we're gonna treat that exactly the same as the side chains. Even though we know reality is different, this is just gonna make your life a little simpler. So we'll say that certainly at pH 7, it should certainly be negatively charged. We're going to say that at pH 2 it's neutral, even though we realize it should actually be 50-50. Does that make sense? Okay. Other questions? Yeah.
Are there specific amino acids that we just won't ever have to worry about the charge regardless if it's pH 7 or 2?
Are there specific amino acids that you don't have to worry about the charge regardless if it's 7 or 2? Well, lysine and arginine both are positively charged and their pKa's are 11 and 12 respectively, meaning at pH 7 and 2, both of them are lower than the pKa, so they stay positively charged. It's it's histidine, H, and D and E whose protonation state can change when you go from 7 to 2. What are the pKa's of the N and the C termini? Of the ammonium group at the N terminus, the pKa is actually 9. If we looked it up, it would be more like 9. And at the C terminus, the pKa is actually 2. For all intents and purposes, we're going to pretend that they're the same as carboxylates and ammoniums in the side chains. So we'll treat the carboxylate at the C terminus the same way we would treat a D or an E. And we'll treat the ammonium at the N terminus the same way we would treat a K and an R. More complicated than that, but that's what we're going to do. Okay, well, this one will be tricky for a couple of reasons. There's some challenging amino acids there, a couple of histidines, and some cysteines. So some of you may have done this. I don't know that it makes sense to have you, it's going to take a while to draw it. I don't know that it makes sense to have you do it and then watch me do it. Should we just all do it together? Is that okay? All right. So remember histidine. The best practice for memorizing the amino acids is not to stare at them and try to get them in your brain. The best thing to do is just draw them a lot. Yeah, go ahead.
Is there a B amino acid?
Oh, dang it. There is not a B amino acid. I thought,
I was like, am I going crazy?
No, you are not going crazy. There is not a B amino acid. That's a trick question. There is not a B amino acid, dummy. Josh. Yeah. So we'll just delete that one. Chuaka. No, we can substitute it with something that sounds like a B. Let's use a V. So like in Spanish, B and V sound similar. So we're going to say Chewbacca. That's how they taught me in the MTC. They said when you say the V, you want to say it almost like you're saying a B. So Chewbacca. Sounds like some kind of cow. This surprised me. I learned this. You may not know this. At least it was in South Texas. The nickname for someone who is named Jesus is Chewy. Chui. Chewy. I thought, is this a Star Wars reference? No. Why are you calling him Chewy? Because his name is Jesus. Okay, okay, all right, go with it, go with it. So, Han and Chewbacca. I can't believe I let my Star Wars get me to overlook that. Oh well. By the way, there is an amino acid shorter than lysine that's called ornithine. It is the letter O. I'm going to introduce it to you at some point on the exam. It's not hard. You treat it just like lysine, and that allows me to spell things like Sith Lord. So, yeah. Already got a plan. Yeah. Okay. Thanks for helping me clear all of that up. All right. So the N terminal, remember, peptides are always written N to C. Thank you, Cambry, for pointing that out. I wouldn't have noticed it. You should have let me reel myself in on that one, because I wouldn't have noticed it till we got there. All right, so, yep, the N-terminal amino acid is histidine. It should be a wedge here, and then it's a 5-membered ring. And it looks like this. It turns out that histidine can exist as one of 2 tautomers. You could put the proton on this side and have the double bond between these 2. Those 2 forms interchange in aqueous solution. They're considered equivalent. So if you forget which side gets the proton and which nitrogen gets the double bond, don't worry, it's fine. Now we need to remember that the pH is 2. Histidine has a positively charged conjugate acid, which has a pKa of 6. So at at pH 2, which is the problem for Chewbacca, pH 2, the pH is lower than pKa, so we should be in the conjugate acid form at pH 2. Sorry, this positively charged conjugate acid form. At pH 7, we would exist in the neutral form, where I'm using pink for pH 2 and blue for pH 7. All right, next one is alanine. That's an easy one. Remember, when you're drawing the peptide backbone for a peptide, it always alternates nitrogen, alpha carbon, carbonyl carbon. Then nitrogen again, alpha carbon, and carbonyl carbon. If you ever get lost or mixed up, just remember the backbone is all N-alpha C. So the alanine should be a methyl group pointing up. The next amino acid is asparagine, which is again like aspartate, only the carboxylate group is amide. And remember, amides are not amines, so we don't worry about the protonation state of asparagine. So we've got H-A-N. Next amino acid is another A, because we need to spell the word and. Very creative.
Does it matter which way you draw the histidine, as long as the double bonds are connected to the right?
Yeah, what do you mean about which way you draw it?
So like, on the bottom structure of histidine, if I flipped it and drew like NH over here.
Right, so you can rotate around this bond between the beta carbon and the gamma carbon. So if you wanted to put this carbon over here and this nitrogen over there, totally fine as long as you get the right connectivity. Yep. All right, so we've got the other alanine. Then I think we have another asparagine, which is boring, but there you go. And then after that, you have D, aspartate, which I think we haven't drawn today. Aspartate is like asparagine, only on the gamma carbon you've got a carboxylate. We need to decide what its protonation state should be at physiological pH. You'll notice my instinct was to draw it negatively charged, but I'm remembering that we're supposed to draw Chewbacca at pH 2. So I'm going to remind myself that aspartate D has a neutral acid form, whose pKa in going to the positively or the negatively charged conjugate base is 4. And so I expect at pH 2, which is lower than that pKa, to be neutral. I expect at pH 7 we're going to be negatively charged. All right, we'll keep going. Now we need a C. C is, I wanted to do some with C's because cysteine is kind of weird. The thing that's weird about cysteine is if you simply memorize that all the amino acids have S stereocenters, you're going to get cysteine wrong. So let's draw the side chain of cysteine. When the nitrogen's on the left and the carbonyl carbon's on the right and the alpha carbon is at a valley, sort of a point position, the beta carbon is a dash, and then you've got an SH group, a sulfur. Now, why do I say you're going to get it wrong if you just memorize the configuration? Let's assign the configuration of this stereocenter real quick. The priority 1 group is the nitrogen. The priority 2 group is either this carbon, which is bonded to twice to oxygen and once to nitrogen and once to carbon, or this one, which is bonded once to sulfur, once to carbon, and 2 times to hydrogen. Sulfur beats oxygen in that comparison. So the beta carbon is actually priority group 2. The carbonyl carbon is priority group 3. That's counterclockwise, but the proton group 4 is up. So we would say the cysteine stereocenter is actually R. Now, that doesn't mean you switch dash to wedge with cysteine. You draw cysteine just like you draw all the other amino acids. Its configuration is R, basically on a technicality because of a priority rule. Cysteine is still an L amino acid. So you're gonna have to find some way to get that right. Maybe all the amino acids are S, except for cysteine, which is R, but only because of sulfur. That makes sense? Okay, so that's cysteine. Let's see what else. We need another H. And again, we've decided that at pH 2, at pH 2, I'm not going to redraw the neutral form. At pH 2, the histidine side chain should exist in its positively charged imidazolium form, and then at pH 7, it would exist in its neutral form. All right, that's C, H. Now we need an E. I'm just imagining if you guys hadn't told me, and we're getting to this point, is he going to notice? Is he going to notice? What's he going to say is the structure of V? So that's E. Here's one that I wanted to do, which is one of the reasons why I chose Chewbacca. Tryptophan is hard to draw. It's difficult to remember. So for tryptophan, attached to the beta carbon, you draw a 5-membered ring. You need no, dang it. Oh, that's right. No, I drew it right. Nope, I drew it wrong somehow. Yep, you're right. Thank you. Nitrogen's at the top. I told you it's hard. And then it's got a benzene ring. So you got a 5-membered ring. The beta carbon's involved in a double bond. Immediately on the other side of that double bond, you have a single bond to a nitrogen. And then you go to this gamma carbon and you make it part of a benzene ring. That side chain is called an indole side chain. You're going to have to draw that one until, but it seemed, yeah, you're going to have to draw that one until you get it. I apparently still struggle, so what are you going to do? All right, the next one is, finally we're there. What's the letter B? Well, we're choosing V as our substitute. That's the valine side chain. Oh, I'm still not gonna run out of space. And then from here on out, we need an alanine, 2 cysteines, which look like this. And then another cysteine. 2 CC, and then lastly, alanine, and the C-terminal carboxylate group we're going to say is neutral at physiological pH. Sorry, let me back that up. We're going to say that the C-terminal carboxylic acid group for our purposes is going to be neutral at pH 2, just like E and D, but is going to be negatively charged at pH 7. Okay, HANANDCHEWVACCA. That's a lot of drawing. But that's a good way to actually practice the amino acid structures. Yes, go ahead. Should the E, yep, also be neutral at physiological pH? Yep, that's a good point, and I did that just by instinct. You're right, the E side chain will be, because its pKa is 4, the neutral acidic form should be the preferred form at pH 2, but the negatively charged form should be the preferred form at pH 7. Great, yeah, good catch. Others? Yeah, go ahead.
On the second C, the one where it's decided to
Yeah.
does it matter which way the S is?
Technically, the S should be the one nearest to the carbon, so I probably should have done that.
But like instead of it going to the
Oh, no, because I can, yeah, your question is it okay to draw it like this? The answer is yes, because the beta carbon is not a stereocenter, and because I can rotate around the bond between alpha and beta freely. Yes?
Would the W also have another hydrogen on it because of the pH 2?
Will the W also have, yeah, so that's a great question, and the answer to that is indoles are also not amines. And the reason for that is the same reason for amides. The lone pair there is adjacent to pi bonds. It's stabilized by resonance. It's not very reactive. It doesn't pick up a proton. So we don't learn a pKa for the W side chain. All right, so we can now figure out what the answer is. At pH 2, it looks like we're plus, neutral, neutral. So overall, that's 2 plus at pH 2. At 7, it's neutral, minus, neutral, minus. Is that right? 3 minus?
Are you adding the hydrogen, nitrogen?
Ah. That was very Palpatine-like sigh. That's like after he's killed Mace Windu, that's what he's like, ah. All right, yeah, we're going to say that pKa is also 11, even though it's 9. Thank you for pointing that out. The positively charged acidic form should dominate at both pH 2 and pH 7. So I did mess up. Thank you for that. And this is what I recommend. Before you select an answer, go back through and check it again slowly to make sure that you've got everything. So I'm looking at pink, since pink is for pH 2. We're looking at, let's see, plus, neutral, neutral. So I count 3 pluses. Is that what you guys count? Okay. And then at pH 7, I count a plus. And 1, 2, 3 minuses. So at pH 7, 1 plus and 3 minuses should be 2 minus. Is that what you guys get to? Okay, good. All right, so that's the kind of thing you're going to need to be able to do. Other questions? All right, now I want to spend the last 10 minutes talking about, and this is what you do, as I've said this before, when you're at the end of a talk and the time is like, you're supposed to be done for the closing hymn at around 5 to the hour, at around I don't know, 11:54, whatever it is, then you need to say, and now, in the second half of my talk, and then just keep going. That irritates audiences all the time. But we do have 10 minutes left. What I want to do is start talking about peptide conformation. What you've seen so far is sequence of a peptide. I guess I should say peptide sequence. And that is something that we call primary structure. That's the basic 1-by-1 sequence of amino acids. But peptide chains have many, many bonds that can rotate, and they will adopt specific shapes or conformations that are also called structures. So localized conformations, short-range localized conformations, is called secondary structure. And this is composed of a few things. Some are called alpha helices, some are called beta strands, and some are called turns. These are specific localized short-range shapes that peptide chains can adopt. When you have association, and we would call this long-range association of various secondary structural units, we call that a peptide or protein tertiary structure. And we say that a peptide or a protein that has tertiary structure is folded. It's just as you can take a piece of paper and fold it via origami to make something that has a particular shape, so the linear peptide chain can change its structure, fold, and not by moving any covalent bonds, but rather by rotating around sigma bonds, can alter its shape to adopt a particular structure. And that tertiary structure, that foldedness, is the prerequisite for function for most peptides. So if you think back to the quiz that we talked about, the mechanism for lipase and the catalytic triad, there was a serine, a histidine, and an aspartate, and I put numbers on each of those, and they were very far apart. One was like in the 150s, one was 190, the other was in the 260s. The thing that brings those three amino acids close together, even though they are widely far apart in sequence, is the tertiary structure of the protein. And this is something that you could spend a whole semester learning about. We study this in my lab. It's really interesting. There's so much I'm like dying to tell you, but I have 10 minutes and then next time. So what we're going to do is, and there's something called quaternary structure that involves two proteins that are on different molecules associating with each other. Just for the sake of definition, and so you can be intelligent humans, I'm going to just define quaternary structure for you. I can't resist. This is association of two or more peptides or proteins. It's intermolecular, meaning two different molecules, two or more different molecules. For example, the protein, the pyruvate dehydrogenase complex, multiple proteins coming together in a complex, that would be a quaternary structure. we're going to focus, we have talked about primary sequence. That's understanding what the letters of the amino acids mean and being able to draw a linear chain like this. We're now going to transition to localized short-range conformations or secondary structure. I'm not going to be able to write out secondary or tertiary as I'm talking and writing notes. If you see me draw this symbol, a 2 with a little degrees, that means secondary. 3 with little degrees means tertiary. 4 with little degrees means quaternary. 1 with little degree symbol means primary. We're going to start by talking about beta strands and turns. So there is an interesting sequence that's been studied by a peptide and protein chemist that is a model for a beta strand and a beta turn. So conceptually, a beta strand is you have a peptide, or a beta strand and a beta turn are you have a peptide that's going along from N to C, and then there are a couple of amino acids in what's called a turn. And then on the other side of that turn, then the sequence continues again from N to C. And the two strands, this part is going to be called a beta strand, and this part is going to be called a beta strand. And this part here will be called a turn. There are many different kinds of turns. The only one we will talk about is a 2 residue or 2 amino acid turn, and it's called a beta turn. And usually there are hydrogen bonds between the strands. Carbonyl oxygens on one strand will hydrogen bond with amide protons on the other strand. And so you'll get that kind of structure. We're not even drawing the atoms now, we're just taking a step back and viewing things. Go ahead.
Is this different than like a beta sheet?
So what I've drawn for you, one beta strand and another beta strand connected by a turn, is the smallest beta sheet tertiary structure. So some people will call beta sheets secondary structures. I think that's imprecise. Because a beta sheet requires at least 2 beta strands, and that requires one strand, a turn, and then another strand. So it doesn't matter. You can use the terms basically interchangeably. People have called this simplest, smallest beta sheet tertiary structure before. They have called this a beta hairpin. To understand that, you have to know what a hairpin is, and you may or may not know that. They're still used, but it's something like this, and then there's a turn, and then there's something like that, and it holds hair, and so you can sort of see the resemblance, why they might call that a beta hairpin. Okay, so the sequence that we're going to draw in this beta hairpin conformation looks like this. Or I'll just write out the linear sequence. Starting at the N terminus, R, W, V, W, V, then an N and a G, and then here's the amino acid I told you I would introduce to you. O equals ornithine. It is like lysine, but 1 carbon, 1 CH2 unit shorter. I don't care that you memorize the structure of ornithine. We're actually dealing with a real peptide that somebody made, so you don't have to memorize O, you don't have to know that it exists. If I want to use it in something to spell something cute that has the letter O in it, and by cute I mean Star Wars, then I will define what it is and draw its structure for you so you're not confused. In any case, O and then K, O, K, then an I, an L, and then a Q. This peptide is unique because the carboxylate, the C-terminal group, you can do this synthetically in the lab. We won't care about how. This doesn't happen spontaneously. Unless I tell you otherwise, you should always assume that the C-terminus is a carboxylate and the N-terminus is an ammonium group. In this particular peptide, they modified the C terminus to become an amide so that it was neutral. Yeah. And then they modified the N terminus. Also, instead of the ammonium group, they put an amide on it. So this was also neutral. People do this from time to time, and it's possible that I will do this too, but if I do, I will tell you and I will make it really obvious in the introduction to the problem. So just read the problem carefully. Unless I tell you otherwise, though, you should assume that the N terminus is the ammonium group and the C terminus is the carboxylate group. So here's the clue. That letter O is wonky. I'm going to show you the two amino acids that are involved in the turn. They are N and G. Do you remember when I told you that G was more flexible than the other amino acids because it doesn't have a side chain? G is often found in turns because of its flexibility. It's able to adopt conformations that some of the other amino acids can't. This part from in orange is the what we will call the N-terminal beta strand, going from R to W to V to W to V. And then this part, which we'll draw in green, oh, that's not green, that's still orange. Green, ooh, somebody was going to say something about that, weren't they? N to C? You're just waiting.
Well, you were going at it.
We didn't want to interrupt.
You didn't want to interrupt the flow. You guys are so nice. Thank you. The green strand is here. So, the way you draw a beta strand, and we don't have time, the way you draw a beta strand is exactly the way we drew it here in an extended linear conformation. But you have to figure out then how to draw the two residue turn, how to draw the other strand in the other direction, and how to make sure there are hydrogen bonds between the two strands. I'll teach you how to do that next time, and your problem set will have you do that a few times. It will be painful, but the structures you will draw will look kind of cool, and you'll be proud of yourself at the end of it. So, pain for growth is the moral of this semester. Have a great weekend. I'll see you Monday.